Good evening and welcome back. Today I didn't write so many things on the blackboard. There is a summary or reminder on the website, but because what we are going to do has almost nothing to do with what we did last week, I decided not to spend time on repeating something that we are not going to use right now. So I just wrote one definition which we are going to play with at the beginning. Okay, so but before this, I need to do some announcement, and it's good it's recorded because for those not here, you can still learn it. There will be a problem, or not a problem, but there is a change of program for the last 2 Wednesdays of this month. So next week, it's perfectly normal. We meet here. The week after, we will meet online. I will not be here. So on the 18th, everybody can come online. I will send the link again through TACT probably. So for those who do not have the link, I will send it to you before, don't worry. And on the 25th, I need to cancel the lecture because I will not be here. Okay. On the other hand, we have still 4 lectures in July. However, usually I stop 1 week before because you start officially the exams start on 24. And usually I try to keep a certain distance or leave you enough time. So, but because I miss a lecture, I need one more. So I decided to do this. The 2, 9, 16, these are regular lectures. On the 23, I will give a lecture. It will be recorded. I make it optional in the sense if you don't want to come, feel free not to come. Of course, I encourage you to come, but I don't want to force anybody to come. It's optional. It will be recorded so you can watch it later. On the other hand, I decided to do a subject because of you, which is about game theory for evolution. There are quite many references also about the evolution, understanding the evolution using game theory. So I will try to make a lecture on this. I usually take a group picture for those students here and also for those online. I will do it on the 16th. And I used to bring some chocolate, but then I have to bring the chocolate only on the 23. So it's up to you to come or not on the 23. But it will be recorded. So if you don't want to come, you can watch it later. Don't forget to submit reports. Not all of you have already submitted one report. So it's really a good time on the... Please think about it. Okay, so what is the last thing we have seen last week? We started a new chapter, which is chapter about games with incomplete information. But the first section is just something I want to mention today. So information model is 3 objects. The information model for 3 players is a set, capital lambda. It's n probability function. So remember, probability. So this is my set omega. A probability function is associate a number on each of these points, and the values of these numbers is equal to 1. The sum, is equal to 1. So this is a probability function. So each player has a probability function on each dot there, and there is also a partition. So it means each player is putting some dots or some points together. And I made 2 here. So we have the red one has 3 subsets, and the blue one has also 3 subsets, but this is an accident. So this is what I'm dealing with. And already with this simple framework, we will see that we can learn something and we can use it later. So this is an information model, a finite set, n probability functions, and n partitions. So be careful, this curly T 1 or 2 is a partition in itself. And I use the letter small omega for an element of capital, small omega. Oh, this is not, no, sorry. I changed, it's lambda. No, sorry, it's lambda. I use small lambda for an element of capital lambda. And an element lambda in this capital lambda is called a state of the world. Important way we name a state of world. So it's how the world is at this moment. Okay. We will see. And so I need to say a few more names. Rho I is called, it's called a prior beliefs. So as I said, it's just a probability function on these dots, on these elements of capital lambda, but it's called prior beliefs for player I. And each tau ij is an information set. We have already seen this notion before. It's an information set for player I, which means that player I cannot distinguish the point. So information for player I, which means player I cannot distinguish this point. Which means he might know that he's inside one of these red set, but not exactly where he is. Okay. And let me introduce a few more things. I will update the website with the information which were here. Okay. Now, if I take a lambda inside this set, this yellow one, think about this yellow dot. So I'm going to call, we denote by tau I lambda. What is it? It is equal to the tau ij such that lambda is in tau ij. So it's just, you know, if you give me the yellow dot, I need to say, oh, the yellow dot for the first player is inside this set, which is, let's say, T1j. While for the second player, this yellow dot is inside this set. So this is tau 2, let's say 2, I don't know. But this is tau 2 of this yellow dot. This is a set which contains this yellow dot, and this is tau 1 of the yellow dot. I think it's understandable. And clearly, if you take lambda and lambda prime inside one of them, Tij, then we have that Ti of lambda is Ti of lambda prime, and of course, this is Tij. So if you take 2 points in a set, when you write this, you just get this set. But usually you don't know a priori where is this, but if they're in the same subset, then you get this. And the last name, any subset, capital E inside this. So if I take now any subset like this one, this is E, is called, it has a name, it's called an event. Is called an event. Oh, by the way, it's the same that is in stochastic calculus. We also call this an event. Do you have any question? So remember, each player has a partition, so a way to decompose this set. And I have introduced, given a point, there is a notation for the subset containing this point according to the player. That's it. So we are going to do two things, so two small constructions with this framework. The first one, I give it for kind of historical reason because it's no more used, but it's quite fun, or okay, you will see. The second one is more useful, but nevertheless, I present also the first one. In order to understand it, the point, it's interesting. You really have to stick to the definition. Don't try to interpret it too much. Just stick to the definition, and then it's rather simple. So I take an event. So it's just a subset. The yellow guy is a yellow subset. And a point lambda in somewhere inside this capital lambda. And we say, just a definition, we say that player I knows E at lambda if this tau I of lambda is inside E. So check the meaning, at least it's meaningful. Unfortunately here, it doesn't apply, so I need to change a little bit. For example, here, it doesn't apply because there is no lambda such that the subset which contain lambda is fully in E. So if I want to have, it's possible, then there is simply, this is simply not satisfied. But if I want it to be satisfied, at least on an example, I need to make it like this. Now, if the yellow one is E, these 2 points satisfy the condition. Oh no, it's not even true. I need to make it even bigger. Oh, yes, the red one, sorry. For the red one, it's good. For the red set is good. So this, now if you take any of these 4 points, if lambda is any of these 4 points, the subset, the red subset containing these points is inside the yellow one. But if you take for the blue player, for the second player, it's not satisfied. Okay, so it's an if. So sometimes it's satisfied, sometimes it's not satisfied. Okay. And then we set KIE is precisely the set of lambda in lambda, capital lambda, such that tau I of lambda is inside E. So on my example, if I take player 1, I can take any of these points, and this condition is satisfied. For player 2, there is nothing. Okay. And you can also, okay, let me keep the picture. I told you, just follow the definitions. It's about how to share the information. And I also set K with a star below of E is now the intersection over I of Ki of E. So I need to interpret this. So if this is a set of lambda such that if I follow the definition, such that I knows E at lambda. Okay, if I just follow the definition, this is what I have to say. And this intersection is a set of lambda such that all players all players know E at lambda, because this has to be satisfied for all players. You take the intersection. It's a condition for all players.
Some players.
No, it's intersection. Intersection I is from 1 up to n, so it's all players.
Null set.
Yeah, indeed, it can be an empty set, and in my example, it is an empty set. But there is no contradiction. Nobody said that this is not empty. Indeed, if in my example, as I said, for the red one, the player 1, we have 4 points, but for this blue one, it's never satisfied, so the intersection is going to be empty. But this section will not be very long. But now you can iterate this construction. And in fact, if you look some old books about game theory, you can see this construction. Because you can continue now. Since KIE and K star E, these are subsets of lambda, right? It's just a set of points. It's a set of points having some properties. So you can iterate. We can consider kjki of E or kjk star of E or k star of k star of E. You just repeat the definition. I mean, there is nothing complicated. Instead of starting with the subset E, now you start with a different subset and you do the same thing. You start with a different subset and you do the same thing, and the same here. Okay. Exercise, and it's not difficult. You just follow the definition. And I will give you an interpretation in a few minutes. Exercise. K star of E is included in K star of E, which means these sets are becoming smaller. And similarly, if you do K star of E, you have M times. So if you do it M times, it's included in K star of E n times. There is not M because n is or P times. And you have an inclusion if M is bigger or equal to P. This is just a matter of writing the definition. And I will denote this. It's almost the end. I will denote this by K star power M of E, which is completely natural. And of course, this one will be K star power P of E, because I do it P times or M times. By the way, can you guess on my example if you continue forever, is it still changing or not? In the sense, do you believe that K star M plus 1 will be different from Km or not? It can be smaller, but look, you have only a finite number of elements. So if you take it smaller, and there are inclusions. If you take it smaller, at a certain point, you have nobody. or it means that you are simply stable. At a certain point, doing some K star, you just keep the same thing. So it means even if I put M large, at a certain point, there is no more any difference. So this is this exercise. And then I give the interpretation, which I took from the book, or definition first. Definition. An event E, which I remind you is just a subset of this, is a common knowledge. It's a common knowledge at lambda belonging to this set if lambda belong to limit when m goes to infinity of K star M of E. And as I said, this limit is meaningful because at most it's an empty set or is just a subset which doesn't change after a certain time. And this notation has a name. It's also called K with the upper star of E. This limit is also called K. What is the meaning of all this? And then at the end. Let's come back to the first one. Remember, the first one, it was lambda, or E is known at lambda for all players. So it's an information that all players have. But then when you iterate, there is one more thing. One more thing is everybody knows that the other person knows. You know that, and it's different. Everybody has the information, you all have an information, or you all know that all of you have this information, it's different. Think about it, you all know a certain number, but knowing that all of you knows this number, it's something different. And this is precisely, so the first one is, okay, all of you have a certain information. The second one is you also know that all the other one have this information and you can iterate. So there is this sentence in the notes. This set here is much more than just people sharing the same information. They share the fact that all of them have this information and you iterate this. I found it quite interesting. And in fact, as I said, part of the theory has been built on this, but it becomes messy because you need to take into account these different iterates. So then apparently somebody, and I will come to this later, completely eliminate this approach and make it simpler. But the original approach of games with incomplete information were based, or the theory was based on this notion. So this is the first thing I wanted to mention. And it's already based on just a small picture like this. The second point, which is also important, so assume lambda belonging to this set is chosen. This is the yellow point. I assume that we have a given point here. So each player, and this is an important notion, each player will update the probability or his belief, I mentioned his belief. Why? Look, at the beginning, they believe that this one, let's say, has 10% chance of coming, this one has 2%, and so on. Now, suddenly, this one is chosen. But the the red player, player 1, cannot distinguish these 4 points. So he cannot say, he knows that, oh, it's inside this set, but he doesn't know which one exactly it is. While for the player blue, the second one, oh, okay, it was the first one. Now the second one, the player blue knows that the state of the world is inside this set, but he doesn't know which one. But he had prior belief. He had already some probability. So now he wants to update his probability. For example, the blue one will for sure put 0 here and 0 here and adapt the probabilities inside this set. While the red player knows that it is in this set, so he will certainly put a probability 0 and 0 on this point and put a different probability here. So this is an update. Each player gets an information. You know that it's inside one of these information set. So you update the probability. So this is what I say. Each will update his belief following Bayes' rule. And I will recall what it is. Following Bayes' rule. Remember, I already wrote this formula last week. The probability of A knowing B is given by the probability of A of B knowing A times P of A. There is a justification for this formula, but I don't want to come to it. So let's look what it makes in our case. So I want to update the belief of each player. So since player I only knows, he only knows that the state of the world, so the one chosen, the yellow guy, the state of the world is inside. And this is why I introduced this notation. He knows that it is in the set containing lambda. So for the first player, he knows that it is in T1 here, T1 something. And the blue one knows that it is in this set, but he doesn't know exactly where. And so, but cannot distinguish the elements inside this tau I of lambda. What he's going to say, he will update his belief with the formula I have written. So he will write for any lambda prime in the set. Now, rho I of lambda prime knowing tau I of lambda. Look, you want to know the probability at this point, which is in any other point, knowing that the yellow guy is in this one. So if I just copy the formula, this is the probability of, I just copy tau I of lambda knowing lambda prime times rho I of lambda prime divided by rho I. So let's interpret this. This is the initial prior. So this is the initial probability. This is a prior, or how I call it, prior belief. Prior probability. Prior belief. This is a prior belief for lambda prime. Now, The second, what we have, if lambda prime is not in this set. So if you know what is the probability of this set, if you know lambda prime, then you have two alternatives. It's either 0 or 1. Look, I said lambda prime is any one. This ti of, let's take the number 1 is this red thing. So if you take a lambda prime outside of this one, of course, it's 0. If you know that, if you know lambda prime is here and you are looking at the probability of this set, you get 0. So it means this is, or on the other hand, if you take a lambda prime inside, you know it's 1. So this is also either 0 or 1. And this is, what is this? This is the probability of this set here, which means it is the sum of these 4 probabilities. Okay, so this is just an application of Bayes' rule, and what we observe that this rho I of tau I of lambda, knowing lambda prime, you have only 2 possibilities. It is 0 if lambda prime is not in this set which contains the yellow guy, and it is 1. It's 1 if lambda prime is inside this set. Because if it is outside, the probability of having this one is 0, while if it is inside, you get just 1. So this is an update, and we will do an example a bit later. But when you know, so think like this. At the beginning, you had a prior belief. All points had a certain probability. Now, you know that the chosen state of the world is inside one of these sets, which is different for everybody. Then you adapt the probability, you put 0 where you have no chance to have this yellow guy, and you update this one. So this is an update of the probability, and in fact, all this chapter is based on this kind of things. Let me just give you an example why we have this. Suppose at the beginning we had 0, 9. This one was 0, 0, 5. And also 0, 0, 4, and 0, 0, 1. Okay. And I just keep these numbers. If you know that now it's inside, of course, your prior knowledge will play a role, because if you know that it's inside and this point had a probability of 90%, most probably it's going to be here, while it's very unlikely that it will be here. So that's why your prior beliefs still play a role, but you normalize with the total weight. So my example is not good because the total weight is already 1. But so think about it. So this is the end of this first section. So if we summarize, I just wanted to give you this idea of common knowledge and the fact that if you have a prior distribution and you get an information, even if this information is not precise, you can update your knowledge. You update this probability. Okay. We are in the discrete case. The Dirac delta function is for continuous, and so you should speak about Kronecker delta. Okay, now section 2, it's games with incomplete information. And we will see what it means. And the big name about this subject is somebody called, I don't know how to pronounce it, Arsène Ni, who got the Nobel Prize in 1994. So he is a person, what he did is he simplified the formalism, which means he eliminated what I mentioned before, these K star of E up to K star of E. So he eliminated all these things and replaced by what is called the type, and replaced them by the types. And I will explain what is the type, what are the types. So he really simplified the theory, and yeah, he got the Nobel Prize for this. And I will present only a simple version of this, but it's enough for understanding what happens. So we shall concentrate on strategy games with incomplete information. What is the difference? It means strategic games. This is what we studied in chapter 2. Players play only once. Player plays only once. While in extensive form games, they play more than once. But we have seen that extensive form game can also be put in a strategic game by taking the pure strategies. So it's not such a big restriction. Let me just say, this is not a big restriction. If we consider the strategic game, this is something I mentioned. If we consider the strategic games based on pure strategies. Remember, we had on extensive form games, we had pure strategies and behavior strategies. But on pure strategies, you can manage to come back to strategic games. And then we can use the formalism of strategic games on mixed extension of strategic games. But okay, if we already understand this, it's very good. If you have any question, please interrupt me, but I haven't really started. So I need to tell you what is a strategic game with incomplete information, and how we want to encode, or how we can encode this incomplete information. So I will describe this. So it's a definition. An n player, finite, and I need to emphasize this because later we will do infinite. Bayesian game and it means, I can directly say, it is strategy games is a strategy game with incomplete information. Why it's called Bayesian? For the following reason. You remember just before I told you we can update the beliefs based on Bayes' rule. For this reason, they are called Bayesian games. So a Bayesian game, which is nothing but a strategic game with incomplete information, is defined by I use BJ for Bayes' game. So it's four things. Oh, sorry. It's four things. Oh, no, it's five. There is one more. So we have five objects. So I need to describe, as I did before for extensive games, I need to define all these guys. Be careful, this is a capital lambda. No, capital theta. Capital theta. The third one is rho, then we have a, then we have a u. So what it is, lambda is a finite set. And as before, it's going to be, I can just mention it, it's the set of all states of the world. But you can think about this like in extensive form game, we had the nature. The nature gave some probability. Here it's the same idea, and I will come back to it. The set lambda contains at the beginning some randomness. So you have the state of the world, which is given by something you don't control. This is the first set, capital lambda. Then we have this capital theta. This capital theta, it's a set of as we have already seen, which means it is a set of all vectors, theta 1, theta 2, to theta n. It's a vector with theta I belonging to capital theta I. And I will assume theta I finite. So, and this is what is called the type. So theta I is called a type for layer I. So it's, and I will explain. So it means this set capital theta is nothing but a type, the set of type profile. Set of type profiles. This is very similar to what we have seen before. You just have a vector, and each player is going to have a certain type. But the trick is that this information will belong only to player I. The other one will not know what is the type of another player. So it's going to be the secret information. But first I describe these five objects. So we have already lambda, we have capital theta, now rho. Rho is a probability function on this set So how you should understand this set capital theta times this, it means you have points, and each point has two coordinates. One coordinate theta, one coordinate lambda. And the coordinate theta is in capital theta. So the coordinate theta is in capital theta. And remember, it's a vector. So in fact, it's n points. N lambda is an element of this set. So this is the element of this. Each point has two coordinates, a first coordinate which is a type profile, and a second coordinate, which is a state of the world. It looks complicated, but we will play with examples later. And now I take a probability function. So it means on the top of each point, I put a number, and so on, such that the sum is 1. A probability function is a function on these points which sum up to 1. So this is a probability function. And this set is finite because, look, this one, I assume it's finite. This one, I have assumed it's finite. So if you take two coordinates in two sets which are finite, it's only also finite. Okay. And in my definition, so we check this one, this one, this one is a set of action. So A is, as before, a product AI, which means it's a set of A1 up to AN, such that small ai is in capital AI. And again, we assume with AI finite. And finally, the last thing is U. I use U all the time for the payoff. I know it's completely abstract now, but we will see that it gives exactly what we want. U, it's U1 up to UN, so it's again a vector. And each of them, now this is a bit more complicated. Each UI is not only a function of AI with value in R. This is what we had before. Now it's a function which depends on the state of the world and on the profile of each player. So it's a function. It's a function of three variables: the state of the world, this profile for each player, and what we are going to see what they decide to do. And then according to these three things, you have a payoff. So this is a payoff. So now this is a framework. Of course, we need to do something with it. Again, the main new object is this profile, the set of or type profile, because it's going to be one new information. The other one are not really new.
Point of A.
We will see. I said this is just a framework. Now I need to say more about each ingredient of payoff function. And I need to tell you how we can represent this object, because so far, just a list of 5 things. So I already said theta I is a type of player I, and this capital theta is a set of type profiles. What is AI? I didn't mention it. AI is a set of actions for player I. Set of basic action, I can see, basic action we will see. And any element and any AI inside this set is a basic action for I. Okay, so now at the beginning of a game, at the beginning of the game, the two things are decided. A state lambda inside this capital lambda is chosen, so we fix the state of the world, so the initial condition. A state is chosen, and a type profile, theta belonging to this capital theta is chosen, but not arbitrarily. But according to the distribution rho. Why? Remember, each point here has two coordinates, one profile type, one state of the world. And you have a function rho, which gives a certain probability for each of them. So if you take at random one point in this set, not all of them will appear with the same probability. If one has a number 909, if you take it at random, you are more likely to take this one than any other one. Yeah, this is true because it cannot be as big as this one. So it means at the beginning of the game, somebody choose a point in this set, but according to this probability. So you have 90% of chance to take this point and only 2% of chance to take this point. And this is known by everybody. This function rho is known by everybody. And each player, this is an important point, each player, so let's say more precisely, the player I and player I knows theta I, but not theta j for j different from. So you really have to understand this point. Everybody knows this probability distribution. So we know that we have 90% of chance to take this one, but it may happen that we take another point. Now, suppose we take one of these points. It has n types, and each player knows one of them. So player one will know, oh, I have this face. This is my face. But player two knows his face, but he doesn't know the other one. He only knows that it has been taken from this set with a certain probability. Is it clear for everybody? We have an initial distribution, then we take a point. Each of them, each player is going to receive exactly one information, but not the other information. But again, as we can update our knowledge, because if we know that, if I know that I have this value, it's already something. So I'm going to change my the distribution row according to my knowledge. I have a partial knowledge, as we had in the picture before. Each player has a partial knowledge. So with this knowledge, the player is going to update his beliefs. So please think about this. And again, we will do an example soon. So at the beginning, we take a point in this set according to this distribution, and each player receives only a bit of information. That's it.
But at least the zero lambda.
About lambda, yeah, this is a key point. Lambda, no, he doesn't know exactly lambda. However, in his information, you can think about like this. In his information, he gets a partition as before. So, you know, we had this partition, it was in the middle. So in his information lambda I, he might know that the state of the world is inside a subset. So he might get a partial information on the precise state of the world, but not a full. And you need this flexibility if you want to cover all situations. So the only information he knows for sure is this theta. This is really the point, but not only for himself. So I still have one more question? I still have some text, and then we do an example. And it's really important to understand it, except the values, the values of this vector theta 1 up to theta n, everything is known by all players. Again, all players know rho, this distribution, and they only know one of these values. So the common prior belief, the common prior beliefs was rho can be updated by each player because they have a partial information, because they know theta I. Each of them has a piece of information. And now what is the formula for this update? I will use Bayes' formula. And this is where I started to fight with the book, because what was written was not correct. So please be very careful, and if you think that there is a mistake in what I'm writing, what I will write, you tell me. So what is the updated belief? For player I, I'm in fact not even using Bayes. I'm just using this P of A knowing B is equal of P of A intersection with B divided by P of B, which is also a standard formula for probability. So what is the updated belief? rho I. Remember, rho was a function on this capital theta times lambda to r plus 0, 1, but all numbers are between 0 and 1. So now we know just one information. So what is the updated belief? It's a function from theta 1 to theta I minus 1. I will explain I plus 1. So look, R plus. This function depends on less variable because you already know one thing. So you don't know, you are the player I. You don't know the type of player 1. You don't know the type of player 2. You don't know the type of player 1, I minus 1. You know your type, so you don't have this variable anymore. And you don't know the other things. So it depends on one variable less. And this is the formula. I want the probability for anything knowing my type. It's the intersection divided by the probability that I'm of type I. Oh, Haruki, please, you check today because I'm not sure about what I'm saying. So it is, again, I forget one variable. It is the ratio of rho of theta 1, theta n lambda. And maybe I should be even more careful. It's a bit surprising the first time you see it, because I put theta I. So it's a function of all variables, which is this guy, divided by a big sum, j different from I, rho j. If you have done some probability, it probably helps. Otherwise, you can find some easy example, and I will give one in a second. Yes, heavy do.
Theta I, which is the type profile.
Okay, so yeah, the notation on the blackboard are not easy. So this capital theta contains all the possible types for player 1. This one contains all the type for player I minus 1 and so on. Now, it means capital theta is just all possible types for all players. And now you take one vector. So you take one element in this big set. And this is theta. At the beginning, we choose one point. And we give the information, you guy, you have this face, you have this one or this type, and so on. But only player I knows the value theta I. So what I'm doing here, and be careful, there is no contradiction. I have the info, I'm player I. I know my type. So the updated belief, of course, I take this into account because I know it. But what I do, it's still a conditional probability because this B is my type. So it's the probability for everything divided by the probability that I get I, and so I get theta I, and this probability I get theta I is obtained by summing all the other variables. So I sum over j different from I sum over all types for player j, I sum over all state of the world like this. So let me give you an example. and you will see that it makes sense. But it's not easy to find this information. So this is an easy example. These two players, each with two types. And the two types are the same, but they could be different. So it means capital theta is made of 4 types. And I use some simple letter. It's XX, XY, YX, YY, because each type is either X or Y. So this first variable is for the first player. The first player can be either X or Y. The second entry is for the second player. And so you observe that you have 4 possibilities if each player can be X or Y. Okay, so this is a set. And I'm going to assume that capital lambda, I cannot say it's empty set, because if it is empty set, we have nothing. So there is a notation when you have only 1 point, you can write either 1, or you can write 0, or you can write just PT. It's only 1 point. It means it's a set containing just 1 point. You have no alternatives. But if you write empty set, it's a bit annoying. So it's either the set containing just 1, or the set containing just 0, or PT is for point. Okay. In this example, we have this. And now what is rho? Rho is a common knowledge. So I need to give it for the 4 possibilities. Rho of XX is 1/6, but it's also rho of YY. And rho of XY is 1/3, and it's rho of YX. Kevidu, please check it sum up to 1. I think so. So I gave, everybody knows this. We have 1/6 chance to get XX or YY, and XY with a probability 1/3. So this is known. Now suppose player 1 receive or knows P is X. So now player 1 knows he's X. So he's going to update. Then what we are going to say, rho 1, because it's related to the first player, it is, let's say I write it in a long way to understand. Second player is X, knowing first player is X. And we have, so now I write it, we will compute it. I also write rho 1 of Y knowing X. So this is a short notation. The rho 1 is the belief of the first player, so it's only related to the second player. So what is the probability that the second player is X, knowing that the first player is X? And what is the probability that the second player is Y, knowing that the first one is X? So be careful, since it is a function about the first player, it's a rho 1, even though this is a variable for the second player. So let's compute this. According to this formula, it is rho of XX divided by rho of XY, rho of XX first, plus rho of XY, because I need to sum over all possible outcome for the second player. And if you compute, I let you do this small computation, you get 1 over 3. While for this one, the computation is now rho of xy divided by rho of xx plus rho of xy. It's the same denominator, it makes 2 over 3. So knowing, and this is really the key point, if you understand this, you understand this lecture. Knowing you had a common information for everybody. Now each of you receive an information, so you update your beliefs. And since the first player knows he's X, he's going to say, oh, then the second player is X with a probability 1/3, and he's Y with a probability 2/3, which is different from what we had at the beginning. Because at the beginning we had no information, now we have one information. But you can also, please do this exercise, also compute rho 2 of X knowing X and rho 2 of Y knowing X, which means now the second player wants to know the probability that the first one in is X, knowing that himself, for example, is X, or the probability that the second player is Y, knowing that himself is X. And then you can do the same thing with knowing that you are Y. So you have 4 sets of things to compute, but there is a symmetry. But in fact, you compute only 1 set because you only have the information about yourself. So if you are X, you don't have to compute the case if you were Y, because you are not. Any question? Again, see, if you are not confident, read this part a few times because it's a key. Yes?
Don't do one move in this case.
We haven't done any move yet. We are just computing some probability. Yeah, I haven't discussed any game yet. So remark, I know it's, but because I go very slowly, in all books it goes much faster. Since theta I is known only by player I, we call this a private information by people. We call it a private information. This is something that you only you have, not the other one. And everything computed based on this, based on theta I, is also a private value. Because you're the only one who can compute this. And yes, even the state of the world, then it depends on the model, but even the state of the world, each player can understand it slightly differently. Come back to the previous section. If you have these subsets which are different, even for the same yellow point, the understanding of the 2 players were not the same because the yellow point was in 2 different sets. So if this information theta I contains some partition of the state of the world, even if the state of the world is chosen, the understanding for each player might be different. But I will not speak so much about this. Most of the time, we will be in this situation. This is the situation in most of the applications. But sometimes it's useful to have something slightly larger. I told you many times you only understand something when you do an exercise. I wanted to give you an exercise because I couldn't do it by myself. But finally, I decided to do it by myself, and I learned it a lot. So let's do this exercise together. No, you really have to do something by yourself. Otherwise, it's just an abstract theory and nothing is concrete. But first, I just write one more thing. It turns out that any Bayes game, so the one I have introduced, finite Bayes game, can be represented as an extensive, this is very surprising, extensive form game with imperfect information. Imperfect recall. Jeffrey, this is a problem for you. Try to prove this statement. It's not difficult, but you have to be well organized. And I will give you an example, and you will see that it's not a proof. I just work on an example, but we will see that we can understand it. But okay, what does it say? It says that any of the games I have introduced here, Bayes game, finite Bayes game, can be represented as an extensive form game. Oh, this is what we have just done. It's a tree. So it's quite funny that we started with a strategic game where each player can only play once, but still we end up with a tree. You will see. It's a tree with imperfect information. So it means that some dots will be connected, but it has a perfect recall. And remember, many results were only true with this perfect recall, which is a very natural assumption. Without this assumption, I discussed with one student, you have some nasty thing in the sense that you may remember part of the past, but not everything. So, which probably is true in reality, but for what we do, it makes it more complicated. So let me give you the tree of the previous example. So just say two games, two players, two types, which are X and Y, X and Y. So I built a tree in the following way. I need 4 starting vertices. Okay, let me do it. I will take more space, so let me do it here. So I start with 4 things like this. Why? Because at the beginning, we have 4 possible choices. Remember, the state or the type profile was made of 4 points. So we have XX or XY or YX or YY. And the start of the game, the nature is going to choose one, but the first player will only know the first coordinate. The second player will only know the second coordinate. So it means now, let's start with the first player is in yellow. But look, I need to connect these 2 things and connect these 2 dots. Why? Because as I said, the first player, this is player 1. So this is omega 1, 1. This is omega 1, 2, because it's the first player information set, it's the second one. And look, it's coherent. The first player knows X, but he doesn't know if the second player is X or Y. While for here, the first player knows he's Y, but he doesn't know if the second player is X or Y, so he cannot say where he is. And now suppose he has two possible actions. Suppose the first player can play A or B. A, B, A, B, A, B. So I should write two players, two types. Player one has two, it was called basic action. And player two, I will do as three, just to make a difference, three basic actions. Okay, so now it's the time for player two to play. So it means this is for player two. But remember, player two doesn't know the type of player one. However, he can observe if player one is going to play A or play B. So he doesn't know the type, but he knows the action. You observe if player player one played A or B. So it means now the imperfect information is like this. You need to connect these 2 points, because look, you know that player A, so you know your type first. You are X for player two. This is X. You don't know if the first player is X or Y, but you know that the first player played A. Or, I take a different color, you have this one and this one, because here you still know your type, you know that you are X, you still don't know if first player is X or Y, but you know he played B. And you have two more connections. So now this guy here has to be connected with this one, because here you know player one play A, but you are Y, but you don't know if the first player is X or Y. And the number, the last one, sorry, it's a bit messy. This is the last one. So it means for player two, you have omega 2-1, omega 2-2, omega 2-3, and omega 2-4. You have, you have 4 subsets. And my claim, or what is here, is that you can always do this if you take sufficient, so the number of edges at the beginning is probably always equal to the number of elements of the space theta times lambda, if ever this is not trivial, but in my case it's trivial. Then you have some subset for the first player, some subset for the second player. And finally, I said the second player can play 3 actions. So you can do 3 things here. Okay, I don't do all of them, but, and then you have the leaves. These are the leaves. So now I can plot all leaves. And this is a tree, an extensive form game. It's an extensive form game because it's like a tree. We have these information set. It's a perfect recall because each player plays only once. This is where it appears. Look, I have only 1 action for first player, 1 action for the second one. So perfect recall is if you play more than once. If you play only once, you have automatically perfect recall. So it's an extensive form game with perfect recall, but imperfect information. And the claim is that you can always do it. But I try to write it, and it's a bit messy. So if somebody wants to do it, you just have to do it systematically. So keep in mind, first player cannot distinguish the type of the second player. Second player cannot distinguish the type of the first player. That's why we have this imperfect or this information set. But he can see what the first player is playing. So there is an exercise where I recommend you to, on internet, you can find some examples or some short videos with examples. Look at one of them, try to understand. It took me a while to do this tree, but this is a way you really learn something. Yes?
You say in this example that lambda contains only one element.
Yes.
And if we had multiple elements, then we had more copies of this graph.
I think so. At the very beginning, you would have, let's say, lambda 1, everything with lambda 1, then everything with lambda 2, and so on. Yes.
And then we choose a direction when lambda is decided.
Yes. But depending on the information you have in your information set, or sorry, on your type, you may, sometimes you know precisely what is lambda, the chosen state of the world, sometimes you don't know. So sometimes you still need to do probabilities. Yes.
And each player partitions the entire set at each depth, right?
Okay, so you anticipate. Look, what about row? On this, so far, I didn't put any probability. So if I want to be correct, at the very beginning of the game, I should put row of xx on this edge, row of xy on this one, row of yx, row of yy. This is a prior knowledge. But now once each player receives the information, I know I'm x. So in this case, I can update. And if I know I'm x, I'm the first player, I will put 0 here and 0 here, because it's if I were y. And I will update these two things, because now I know that we are here. While for the second player, he doesn't know at the beginning, but if he's, let's say, x or y, he will again choose some branches according to what he is, and put 0 elsewhere, and update his belief. So the two updated beliefs can be written now on this part. However, they will be different for the two players. That's the point. There is not a common, once you know your type, you will update this part because you have an information, and this will be known only by you. It's a private information. What is common is the initial distribution. Once you update it, it's private. But it makes a big difference, because if you have some payoff here, we have seen that depending on the probability, you get different payoff. So each player will have a certain information about the payoff, which is different from the other player. I will continue with this next week. I really encourage you to read this once or twice. I didn't do so much today, so it's probably only everything is on 2 pages. But next time we are going to do an example, a concrete example about auction. But it's good if you know this terminology and have a good idea about this. I find it interesting because, you know, it's a way how to encode. We want to describe something with a partial information or incomplete information. How to build a formalism which gives you this possibility. How to find a framework where you can easily, because finally it's rather easy, you just put a new variable which is this theta I. You put all the secret information in this theta I, but the rest is known. And you can continue. So please read these few pages, and if you have any question, ask me. If you can also look at the formulas I have written, and if you have any doubt about this formula, let me know, because I might be wrong. This pencil, it's yours. You can correct it. Yes, one fact.
Why can't we continue the game?
That's what I said at a certain point. I do it for strategy game, because already if we understand this, it's good. Then indeed, the next step would be to continue on it. Yeah, as you have already everything, because there is only one step where you get your type and compute everything. Then it would be just a regular tree. So you can just continue as in the previous chapter.
And the row function is now player dependent after the first group.
The row function is updated because we have each one has a different information. Yes, this is a difference.
But will that affect it that we can't continue, or will?
No, it will, we can continue. Simply, I cannot write only, I mean, I can write the common distribution at the beginning, but each player, because they get some information, are going to update. So you do your small computation without showing it to anybody because you have this information and you want to keep it secret.